Ladies and gentlemen, we are moving to the next session. It's my great privilege and honor to chair this session. I thank very much Mr. Nešković and the rest of the organizers to be the part of this great meeting. And I'm very honored to chair the session with the four distinguished presenters and the exceptional presentations. So just to remind you, we have 15 minutes for each presentation, and then we'll keep the discussion part and the comments and all debate after the session, altogether 1 hour and a half. So I'm very much pleased to call Mr. Aleksandr Bugay from Russia, Dubna, to deliver his lecture. Please.
Okay. Good day to everyone. It's my great privilege to deliver this talk. Actually, I'm representing not Russian Federation itself, but the international intergovernmental organization called Joint Institute for Nuclear Research. We are like Eastern CERN, so we are we have members from a lot of countries, from different continents. So let me proceed to the topic itself. It will start probably from the art and scientific fiction picture. So the mankind and every human probably always dreamed of space travels, exploration throughout our universe. Almost 100 years ago, we expected that, let's say, in a few years or in tens of years, we will reach Moon, Mars, and so on and so forth, build colonies. And now, engineers from different space agencies said, well, if speak honestly, this is true. We can do it technically. But what's the problem? The actual problem is that we underestimate some important effect. Namely, one of the main problems is the biological factor and influence of radiation during the travel itself and also on the surface of some planets. And so, what is the problem? Actually, almost everyone knows about solar energetic particles coming to the Earth, producing magnetic storms and so on and so forth. Our satellites also could be damaged by these solar-induced events. But if we come even further up to the Moon and to other planets, we eventually will be held under very harsh radiation conditions. Not only solar energetic protons and other particles will reach the spacecraft, but also very high Z and energy accelerated ion species, up to a group of iron and other elements. Of course, the amount is not so huge. It's about 1% per energy and flux. And the dose delivered to the astronaut during the travel is rather low. It's under the limit for the pilots who work on space orbits and so on. But what's the problem? Actually, those energetic particles have very different biological efficiency. So they produce very harsh damage to biological systems, and we need properly account this radiation factor when we plan such long-term travels. Also, another problem, we cannot construct very efficient shielding from these particles, because then they hit very thick shielding. They produce also some particles which have short ranges, and they are even more biologically efficient. So this is a very dangerous factor. We know that there are different sources of such kinds of radiations. I will skip the whole explanation. So the most problem is coming from this part, with very high energies and very high Z. So on what to do? Of course, mankind tried to simulate all these radiations. It could be done only on very huge accelerator complexes, mostly built for the purposes of basic sciences, particle and nuclear physics. But there is still a problem how to properly simulate all those space environment, because in typical real-world experiments we have monoenergetic beams of specific particle used in physical experiment, but in space we have a mixture and prolonged exposure. So now there are several complexes all around the world trying to reproduce those effects. NASA probably was the first, then Germany and our institute also had a lot of investments. This is the facility where we work with heavy ion beams, newly reconstructed, so we also invite users from all around the world. And what are the problem here? First, we need to properly reproduce space experiments, as I mentioned, so we need to reproduce particle spectra using specific ion sources or specific target convectors producing such condition for irradiation. But the problem really is the impact of these radiations on living organisms. Of course, we can study it on humans by ethical reasons, but still, there are a lot of known effects how the radiation can act on living organisms. The first known effect is the origination of biological damage, especially to genetic structures, and induction of mutations that could produce stochastically cancer and some other hereditary effect. So this is one of the key factors traditionally being considered for the estimation of space travels. This is how it looks like on the molecular scales. Radiation produces ionization, free radicals that are attacking DNA, producing very strong clusters of damage. And for those space particles, we have even stronger impact on this molecular scale. We have very tightly bound clusters of molecular lesions that are hardly to be recognized and to be repaired. And the reparation of such complex events always proceeds with a lot amount of error, producing so-called producing mutations and chromosome rearrangements, so-called chromosome aberrations. So in this case, we will get a very complicated reconstruction of our genotype. You see a normal picture from fluorescent microscopy and a very harsh and complicated rearrangements in a single chromosome, containing up to more than 3 individual fragments in one. So if you compare typical gamma rays and protons and what we have in the space, primary particles or secondary neutrons, we will get very strong impact on the mutagenetic profile and genetic instability. What is the result? We expect a lot of cancer induction. And specialists from NASA, for example, computed the risk for the cancer induction, and indeed for the long-term space travel, it will grow several times in several orders. But what is at the other hand? At the other hand, we have another problem, impact of radiation during the flight itself. It's not a delayed effect like a cancer, but this is an ongoing process. There are a lot of known mechanisms. Unfortunately, I don't have much time to go deeper into the details. We can touch them upon the discussion, but there are a lot of experimental evidences, both on molecular level, on the level of neural cells that are hardly damaged after such a radiation exposure. There are a lot of knowledge about generalized processes like neuroinflammation after heavy ion irradiation. Of course, a lot of problems emerging in behavioral reactions and neurodegenerations, which is closely connected with some brain diseases. So the radiation potentially could induce some problems like Alzheimer, for example. So we see here typical traces of Alzheimer's disease. And the animal behavior strongly degrades even after several months after the irradiations. At different centers, the people and scientists studied. Oh, sorry, I probably missed something wrong. Okay, thank you. So, and what we did, we did even very unique worldwide level experiments with very complex organisms like monkeys, and they clearly demonstrated that impact of such energetic and high Z in energy particles would be very damaging, even at very low, non-extreme, non-killing doses. And after the several years, after years of irradiation, the monkeys all are still alive, but we see that there is a huge level of chromosome rearrangements, and in some animals demonstrated induction of cancer, especially brain cancer, and also some of the animals in the reproductory demonstrated that they behave abnormally. So this is not a typical behavior for this species of monkeys. So on what we want to do, how to protect? Of course, we need some investment in physical protection, especially maybe very strong magnetic fields based on superconductor technologies, or maybe water and polymer-based screens. This is still ongoing progress, but still no technical results. Another point is to develop radioprotective drugs. Still, there are no such drugs for heavy charge particles like protons and heavy ions. There is still a way to do for pharmacy. Also, a lot of people now discussing hibernation problems. Maybe we could put organisms in a resting stage so it would recover after the space travel, but unfortunately it works only for sparse ionizing radiation, not for heavy ions. This is still a problem. Or maybe we should go into genetic engineering, like some science fiction says, maybe to grow a cohort of professional astronauts, but unfortunately, will it be a human or not? How picture from science fiction movie says, we actually don't know how it will be. But there are still some positive traces, whether the life is still there or not. And also I would start with some speculations. These two guys, Professor Richard Hoover from NASA and Professor Alexei Rozanov from one of the Russian institutes, tried to study meteorites in order to test panspermia hypothesis. And in recent years, indeed, they proved that there are a lot of organic remains in the particular meteorites. This is called Orgyle, found in France. So potentially the life is still there. At least it may be found. And also there is some complex and abiogenic synthesis chemistry that could be induced by this kind of irradiations. And still, if you model these processes with, like we say, astrochemistry, we may find very complex organics found on the soils of meteorites and planetary and so on and so forth. So potentially the biosphere and life has the conditions how they could emerge and how they could travel. But what is the idea? The simplest life potentially existed, or maybe even exists somewhere in the universe, and it's capable to endure the space travel, potentially. No one had proved it yet. But how we can know it for definitely? Without solving this radiobiological problem, the danger of radiation factor, we cannot advance further in the space exploration. And this is a challenge. This is a challenge for our development, of our knowledge of universe and the development of the mankind. So I put these questions to be addressed in the future development. And this is the end of my talk. This is the team of our laboratory who do biological science from different countries. And also I have some advertisements on International Conference on Biological Physics promoted by IUPAP, Biological Commission from the IUPAP. And also we launched a new journal, fully electronical, to support open science. There are no fees, no publication fees, no charges. It's completely free. It's online peer-reviewed journal, so there are some pamphlets on the table here, so we can apply a review a regular article. That's it. Thank you for your attention.
Many thanks. We'll move to another presentation, and then we'll have at the end, like I said, the discussion. So the next speaker will be Zhou Detai from China about the control and safety system in Chinese initiative accelerator-driven system.
Yes. Okay, good morning, Professor. I'm Zhou Detai from the Institute of Modern Physics, and my report is about the Chinese initiative accelerator driving system. Today's talk focuses on CiADS's core value, technical position, development progress, and strategic significance, offering a concise overview of the national strategic infrastructure. Okay, today's talk has five key sections: background and value, positioning and composition, control system, a timeline, and summary. This section places CiADS in the context of global energy transition, explain its core necessity. Look at this pie chart. From the 2024 global energy consumption structure, fossil fuel still account for 86%, forming the backbone of the current energy system. But this also means we urgently need low-emission alternative like nuclear energy. Non-fossil energy is growing, such as nuclear, hydropower, renewable, but not fast enough to meet net zero goals, which is where CiADS and value. China plays a key role in the clean energy transition. In 2024, China contributed nearly 60% of the new renewable energy supply in the Asia-Pacific region. This leadership makes China the ideal location for CiADS, a facility that will further accelerate the energy transition. Nuclear energy is essential to global net zero. Without nuclear energy, net zero goals will be hard to achieve. It is a mature, low-emission energy source that effectively de-electricity electricity system. An advanced nuclear facility, CiADS will strengthen this role, especially as China becomes the world's leading nuclear power producer by 2030. Next, we focus on two national major science and technology infrastructure in Huizhou City, Guangdong Province, with a core focus on CiADS. National major science and technology infrastructure are national strategic assets for technological self-reliance. China plans to build 2 facilities in Huizhou, the heavy iron accelerator facility, we call it HIAF, H-I-A-F, and the Chinese Initiative Accelerator Driving Subcritical System, we call it CiADS. HIAF is the world's most intense heavy iron accelerator, while CiADS is the world's first megawatt-class ADS system. Together, they will enhance the greater Bay Area's science tech innovation capacity. Key information on the 2 facilities. CiADS, the world's first megawatt-class ADS system for use on self-reactor operation and capped transmutation, with a total investment of 40.60 billion yuan. HIAF, the world's top heavy iron accelerator used for heavy iron physicals research, with a total investment of 28.71 billion yuan. Both are national strategic facilities, help China lead in advanced nuclear energy and particle physicals. This section analyzes the core positioning and the key components of the ADS facility. Focus on CiADS technical core. The core value of ADS lies in 2 major pain points of nuclear energy. The first, safety. It uses an accelerator to provide exterior neutral, enabling the reactor. Enables the reactor to operate the subcritical state, greatly enhance safety. Second, waste disposal. It can transmute long-lived radioactive waste, addressing a key bottleneck for sustainable nuclear energy, which is also CiADS core goal. CiADS key technical goal is realizing megawatt-class ADS capped operation and having first of its kind demonstration value. The ADS facility consists of three more modules that work together to support its function. 1. Superconducting linear accelerator. It produces high-energy particle beams. 2. Spallation target. Generates neutrons through beam target interactions. 3. Subcritical reactor realize nuclear reactions and transmutation in a safe state. Other system is clean system and control system. The control system is the the central New World system of ADS with two core rulers. First, safety line of defense, real-time monitoring of abnormal parameters to trigger alarms or emergency shutdown. Second, coordination link synchronizes the operation of the accelerator, simulation target, and reactor to ensure system stability. We use APICS as the control standard for ADS. APICS means experimental physics and instructional control system. APICS is a global collaborative project with real-time data transmission capabilities, ensures the reliable operation of ADS. As an industry benchmark for large-scale control system, APICS is adapted to the complex control needs for ADS. To ensure ADS safety, we follow the safety standards. We adopt IEC 61508, which is widely used in safety critical fields such as nuclear industry and medical core. This tries to ensure CiADS meets safety requirements. We review CiADS core development milestones and interpret its strategic value. CiADS has clear key development milestones and steady progress. 2030 included in the National Long-Term Plan for Major Science and Technology in Infrastructure, establishing its national strategic. 2015, approved by the National Development and Reform Commission, officially launching the project. 2024, first beam granted at the LINAC front end, achieving a breakthrough in core technology. Target 2027, completion of construction and entry into trial operation. CiADS strategic significance lies two core aspects. First, solving nuclear energy bottlenecks by transmuting long-lived nuclear waste. It clears obstacles for the sustainable development of nuclear energy. Second, contributing Chinese solutions to global decarbonization. A brief summary of CiADS core value and progress with an outlook on future cooperation directions. CiADS is a safe and advanced nuclear facility that not only solves the nuclear waste problem, but also leads ADS technology. The 2027 completion target is clear, and we welcome global research institutions to participate in cooperation to jointly advance the Goal Net Zero programs. Okay, CiADS is China's important contribution to the global decarbonization course. Thank you very much.
Thank you, Mr. Zhou. Detai, I'm sure we'll have some time after the all presentations for the brief discussion. And now I'm calling Mr. Dejan Trbojevic from United States, Upton, New York, to deliver the lecture on the accelerators of the ion cancer therapy.
Just a little bit an introduction. I'd like to thank to the organizer for letting me say a few words about this subject. It is kind of connected with it's a small contribution to the problem of energy reduction. At this time, it is for the cancer therapy treatment. My background is actually starting from this town, where I started to work on building accelerators, the small one at electrotechnical faculty. Then continued at Vinci Institute. We had 150 MeV EMA, and continued with doing the same things in United States in Georgetown University, 1.5 MeV, and then moved to the Fermilab, where the accelerator was the largest at the time in the world, 400 million electron volts, GeV, which is an order of magnitude higher, and the Tevatron, which was 1,012 electron volts, moved to the Brookhaven to be the head commissioner of the relativistic heavy ion collider. So in essence, I worked on the improvement of accelerators to the whole my life. This is a part of the spin-off of this work on the accelerators to use it for cancer therapy. I have a very short time, and for the wide audience, I'd like to explain what is, first of all, cancer therapy and where are these contributions important. But before doing that, to connect this project to the real limitation of planet existence, I have to connect where this contribution comes from. So that I'll explain a couple of slides of why is in the global warming reduction of energy and use other energy resources critical to existence of the planet. Then I would like to explain a little bit of why is ion radiation better to use than existing most of the radiation in cancer therapy are X-rays. Then I will show you a few contributions in fully energy efficient system with 99.8% energy efficiency we build as a proof of principle of how the accelerator should be built in future. You heard today about the FCC project at CERN, so this is also connected to future accelerators, because in today's world you have to look at how to save the energy and how to reduce the consumption of the production of the carbon dioxide. And then I will show you the new radiation treatment, promising treatment, which is in experimental phase, called flash therapy, and why this accelerator I am proposing is the only accelerator in the world which can do the flash therapy without a problem. So this talk today about the carbon dioxide, how bad it is for the human life, not only it is bad for human brain, but it is a main problem why the global warming occurs. Because, as you can see on this graph, we were stable, the planet was stable for a long time until in the last 50 years started to go very substantially up due to the use of burning the fossil products of many natural resources, especially oils and coal. So that resulted in the temperature rise, which is very clearly shown in the last year. So the only way to deal with this problem is, as the previous talk said, we need to go to the other sources of energy which don't produce carbon dioxide. Carbon dioxide is coming from the energy use by burning the existing natural resources. So we have to reduce that. So my contribution is I would like to use the system where I'm going to reduce the energy as much as I can. So now I'm going to switch the subject for the wider audience to understand why is the ion therapy better than the X-rays. X-rays are mostly used today in treatment of the cancer because 50% of the cases in cancer require radiation. So most of the radiation is done by the X-rays. The problem with that is, you can see on that graph, the X-rays go through the body without stopping anywhere. In the case of ions, you can see that there is so-called Bragg peak, which is shown on the picture. As the ion go through the body, most of the energy is deposited exactly where the tumor is. So that's the main advantage of using the ions in the necessary radiation treatment, because ions do not go further than the Bragg peak. And you adjust the energy of the ions such that they go exactly where the tumor is. If the tumor is wider, then you have to do the spread out Bragg peak, which is shown in the lower picture. So you have two kinds of ions today used, mostly two, but there are other uses of the smaller size ions like lithium and others, but most of the cancer therapy treatment with ions are in United States are with protons, but carbon ions have a little bit better radiation damage, which is shown by this number, RBE, radiation efficiency. And you can see that the peak is very more narrow, so the energy is deposited more precisely in the longitudinal space. So because of these advantages, the number of facilities is growing exponentially up. Right now, there are about 150 facilities around the world. In Europe, there are many. About 6 is using carbon ions. In Germany, there are 2. In Italy, in Knau, there is 1. In Austria, in Vienna, there is another carbon facility. But most of the patients in today's world are, I think it's already 500,000 is using ions because of these advantages. You can see where are distributed around the world. So in addition to the longitudinal scanning, which depends on the energy, you have to do the transfer scanning to be more precise, where to hit these tumors, you have the pictures of the tumors, cancerous tumors. So when the ion deposits the energy, it destroys the DNA of the tumors, and that is the reason why they're used. So how do you do these treatments? How do you produce these protons and carbon? And how do you accelerate them? Because you need about 250 megavolt energy to get through the 20 centimeters, 25 centimeters of the human body to be efficient and do the deep-seated tumors. To do that, they use mostly proton cyclotrons, as they shown in this picture. The smallest one is Mayo. Recently, they removed that rotating device where the Mayo, the cyclotron is above the patient due to the side effects of neutrons. Now the accelerator is separated from the patient. And that 1 meter diameter of the cyclotron is possible to do because they're using niobium tin, which is superconducting coil, which produces 8 Tesla field. It's a very strong field to be able to bend the protons and accelerate them to this energy. The problem with cyclotron is this energy coming out of the cyclotron is always the highest one. To get a lower energy, you have to go through the target, so-called degrader, to reduce to the energy you need. That degrader is a bad side of the cyclotron use because the emittance, the beam gets larger and the intensity gets smaller. There are, of course, the other ways to accelerate particles. These are the synchrotrons. They are used also widely around the world. The first one was in Loma Linda. We built that one when I was at Fermilab and delivered them to, this was the first particle accelerator using protons for the patients. There are others, like in Vienna, shown Medostron. It's a similar cyclotron as it was built in Darmstadt in Germany. They are using for protons and for carbon ions. You see the size of that gantry on the Heidelberg facility. It's enormous, so that has to be reduced too, if possible. I did some work on that as well. So these are the ways how you have these particle accelerators around the world, and they are this type available. Now I'd like to switch the subject to a new, recent, in the last 10 years, experiments on the new way of radiation. It's called the flash therapy. These are the results from the Russian scientist Gritskova, where it shows you that the regular proton treatment has some problems as the ions go through the body. They do the radiation damage getting up to the tumor. And that is a problem. So to eliminate that problem, suddenly they realized if you raise the radiation from 2 grays per minute, usually used in the regular proton therapy, to 40 grays in second, and do that very fast, then the live cells on the way to the tumor somehow recover. There are a couple of theories why this happens. One of them is the oxygen deficiency, that cells can recover. That new flash therapy is becoming very exciting. They are doing multiple experiments on animals. We will be radiating in next week 23 mice. Half of them will be with the regular proton therapy, and half of them will be treated. They have tumors in their prostate. They're male mice. And we will try to see the difference and try to catch the optical signal from oxygen to prove that this is the reason of the recovery, if there is a recovery. So it's still being experimentally tried. On the left side of the picture, you see the regular cells magnified. In the middle of the picture, you can see that's results from Gritskova, where you can see the damage occurred with the regular proton therapy. You can see on the left and right side of the cells. But on the right side of the picture, you can see how in the flash therapy, cells look more or less like in the normal conditions. The same thing is shown in the lower picture. How am I doing with the time?
You have to ask the chair.
Pardon me? How am I doing?
We're okay. We're okay.
Good?
You can
Okay.
continue.
The problem with the existing proton therapy facilities and carbon therapy facilities is multiple. Because of the time that they have to go through the degrader, all the facilities with the cyclotrons have a problem of making in 100 milliseconds the beam you need to do very fast radiation at the specific position of the tumor. In the facility I will be showing you, I am proposing there are no limitations in that. I can do everything in 100 milliseconds with the 4 gray. So that would be 40 grays per second required for the flash radiation. The problem with the synchrotrons is they have very long so-called, they reach the energy you need and then they take the ions out, but to do any difference in the positions, you need to change the magnetic field to get where you have to be and where the energy needs to be. Any change in the magnetic field has a problem because of the hysteresis, so you cannot do that in 100 milliseconds. You need minutes to get the right field. I don't have that problem because my magnetic field is fixed in the whole energy region. These are all facilities, and I'm showing my proposal on the right side, how everything can be done correctly in the flash. To prove that proof of principle, we were investigating the new collider for electron and ions, and we made a small sample of that collider in the Cornell University, where I was the leading PI of this project, to prove that we can do accelerate the particles with one single ring for multiple energies. And we got the money from the New York State, $25 million, and we were able to finish this on time and test the machine to show that this works. This accelerator is going to be on the same principle as you saw the 90 kilometers proposal for FCC. They will have to use superconducting cavities and superconducting magnets to be able to do these things. Unfortunately, that proposal for CERN requires a lot of energy, which Europe presently doesn't have. So that has to be investigated, how to reduce the required energy. So what is interesting in this project I did is that the permanent magnet loop transports 4 different energies at the same time. This concept I came out with in '99, and it's shown in these pictures how in the permanent magnets with a fixed magnetic field, you can transport with so-called non-scaling fixed field machines, alternating gradient, 4 different energies at the same time. So these are the details of this project, how we we came up with a new way of making these Halbach type magnets to do this alternating field. We correcting the field with these correctors, and we build these magnets in Slovenia in a very good company, Kima. We installed them and we measured them. We showed that everything worked as predicted. So this worked very well. Now, based on that, I made a proposal to build this for the flash therapy facility, which is shown here, presented this at multiple conferences. So what is the proposal for the facility? You have to have an injector. which can be a small cyclotron. You have to have this ring made of permanent magnets transporting all the energies at once. You have to have a gantry also made of permanent magnets, shown at the last place. And these are the injection cyclotrons, which are available on the market. You inject and you extract the beam standard way. This is the ring presented in the details. You merge the orbits into one after the arc. And we built these magnets for the synchrotron. I got support by the lab, and we tested them last week. They have to have fixed tunes to be able to go 6,000 turns. And these are the measured and predicted fields. And these are the magnets, which are this big. And we installed them, and we've transported all these beams necessary for the particle therapy between 50 and 250 MeV in the first time, and then we measured it with between 10 MeV and 250 MeV, prove the proof of principle, show the concept works. The gantry is already shown that it works very well in the energy range for treating the patients, so you don't need to change the magnetic field, and you can deliver the energy required for flash without any change of the magnetic field, which is the major problem for any existing facility. These are the conclusions. I can do that with just 3 times less money than presently required for any other machine on the market. And I also have some other, we are going to accelerate the beam in the lab with mice. I also have proposal for the same kind of magnets used for the electron-proton collider at CERN. This was presented at CERN conference, and we are presently working on using the same magnets. And at the Jefferson National Laboratory, we got the support for that. With a single beamline, we will double the energy of the existing fixed machine at Jefferson Lab. That's all.
Thank you. Thank you very much, Mr. Trbojevic. We're moving to the last not least presentation by Professor Aleksandr Terzic from Rochester, Mayo Clinic, about the health span and the lifespan gap.
Thank you so much for the invitation, and indeed, many thanks to the leadership for all the effort they are doing in advancing the cause. What I will be touching today is upon the work that we're doing at the Mayo Clinic in terms actually of a global question. The question of the day is what unites us all is that we live longer. And that's shown in this couple of panels. On the left side, you can see in the bar graphs, the population of the world is now at 8 billion. And the blue line shows that the biggest acceleration actually in the growth over the recent years has been particularly for people that live longer than 70 years of age. In fact, on the right panel, if you regroup them per countries, you can see that while in the past there were very few countries that had larger populations of older people, increasingly the number of older people is definitely increasing in countries around the world, and the projections are this will increase even further as we go forward. So that's in a way the good news. In fact, this is viewed as a global achievement because it's true throughout the world, across all the continents. And some have even called it the triumph of humanity, that we live longer than our ancestors. but there is a price to pay for living longer. And the price to pay is something that we have recently measured. If you look on the left side, we have used the United Nations classification of the world. They classify the world by 6 regions, which are both geographical but also societal and historic. And the red is what I told you already. We live longer. That's what we call the life expectancy or lifespan. And it's true that for all countries and all continents, we live longer. But the green is what is lagging, has not reached that level of extension. And that's the number of years that we live without disease, free of disease. And that's what is called the health span. And we have coined that term. The difference between lifespan and health span is the health span gap, or lifespan health span gap. And the gap basically is a measure of the disease burden, or a disease and disability burden that we have. So in the right map, you can see we mapped the gap for the world, for each country. And again, it's present throughout the world. Some countries have bigger gaps than others. In the lower panel, you can see, for example, the United States has the largest gap than any other country in the world. They have a big load of disease. But on average, the globe lives roughly a decade burdened by disease. So all of our lives are burdened roughly by 10 years that we are burdened by disease. The exact number, if you're interested, is 9.6. It's worse in women, unfortunately, and that's the price the women are paying for living longer than men. They live longer than men, but unfortunately, these extra years of life are not free from disease. In fact, there are many contributors to the Healthspan-Lifespan gap. One is life expectancy. That's the most obvious because aging is a risk for disease. But there are others, for example, the economic status, the socio-economic situations in general. So it's possible to predict what should be the Healthspan-Lifespan gap based on these other factors. And it's possible for each country of the world to see if they are doing better or worse than they are expecting. So on the left are all the countries that are doing worse than expected. They have larger gaps that exceed what can be expected, let's say, based on their life expectancy. And rather than reading, which is difficult, each country, actually per region of the world, the majority of countries that are doing worse than expected, unfortunately, is in Africa. They have maybe small absolute gaps, but those gaps are still much larger than expected. On the other hand, on the right side are those that are doing better. They have smaller gaps than expected, and I try to highlight Serbia in blue. It's difficult maybe to see, but Serbia is among the actually countries that are doing pretty well by having a smaller gap than expected. But regardless whether you're doing better or worse, your gap, regardless where you live, will keep on increasing, will keep on growing. We're using the term will keep on widening. The Healthspan-Lifespan gap will widen, and here we measured it and projected it into the next century. And so it's true again for the 6 regions of the United Nations. On average, it will be at least 20 or more % will further grow. So that will be the major challenge that humanity collectively will have to face. We can celebrate the longer life, but we'll have to deal with a gap that is burdened by disease. And so one step in addressing that question is actually what we did here. We clustered every single country to see if there is patterns that we can predict the disease burden that underpins the gap. And interestingly, using artificial intelligence, you can cluster the 183 countries, or to be correct, they're called member states of the World Health Organization, they cluster into 3 patterns of diseases that underpin the gap. So you can divide the world in different ways, in political, in socioeconomic, but you can also have the 3-partite division based on disease patterns. And one pattern is a pattern more specific for countries linked to Africa, another is more specific to Europe, and then the third regroups the rest of the world. Each of these gaps has a specific length and a specific disease pattern. So if you tell me where you live, I can tell you what type of diseases you are burdened with, and vice versa. If you tell me what diseases you have, I can tell you where you live. So that's a starting point. So for the World Health Organization, they will not have to worry, or for national even centers to worry to develop strategies for each country. In principle, it can be concentrated on finding solutions for these 3 patterns, but it also means that there is not one solution for everybody, because there are unique identities, as we can see here. One common theme is, again, regardless where you live, the burden of disease will keep on increasing based on chronic diseases. Chronic diseases are also known as non-communicable diseases, where you cannot pass them to another person. Chronic meaning that they are lifelong conditions. One of the worst diseases is cardiovascular disease. It's linked to conditions of the heart, the vessels. And it alone, cardiovascular disease, is responsible for 1/3 of all deaths worldwide. So around 60 to 70 million people will die this year in the world. All reasons combined, including diseases and beyond diseases. 1/3, like over 20 million, will be due to cardiovascular diseases. And among cardiovascular diseases, just to take today an example, heart failure will be a dominant disease. It's already affecting 1% of all adult population in the world. So if you take the 8 billion number that humanity is large today, around 80 million people suffer from heart failure worldwide. So that's not the next epidemic, not the next pandemic, it's the current pandemic. And it's where the world is increasingly focusing. And members actually of the Serbian Academy were among the members that were part of that world effort in trying to understand the magnitude of the problem. And the magnitude can also be seen on the right. If you take every 4th person among ourselves will unfortunately develop heart failure during their lifetime. So prevalent is the disease. Just to give you an idea, cancer is also a very dramatic condition, but it's 1 in 8. So heart failure is 2 times more common than all cancers. Now, we have remarkable tools to address the heart failure issue. We have drugs. In fact, in recent years, there have been a revolution in new drugs for the treatment of heart failure that have been truly modifying the disease itself, which has not been the case in the past. There are also devices that are very important because they are life-extending measures, and indeed transplantation, which is in many ways an exemplar of extreme ways of treatments. But these conditions are bringing us to think, are they truly sustainable? And the concept of sustainability is summarized in this slide, at least the way we see it right now. So transplantation is a concept that invites us to think, can we recycle an organ, in this case a heart, to reuse it? Another concept will do, can we do better than that? Can we upcycle, in other words, add value or transform even a diseased organ in order to repair it? And ultimately, can we recreate a path to new destiny and from a diseased heart reclaim health? That will be the ultimate direction. And I will highlight each of these examples, but what is common and what will be the final message is the sustainability will most likely come from within. We ourselves, as individuals, will be ultimately responsible for a sustainable solution of our own issue, which we will discuss through these examples. So, as mentioned, transportation has been a remarkable breakthrough. And because we have also members from Africa today with us, actually the first transplantation was done in 1967 in South Africa, in Cape Town. It's a remarkable technology that has evolved, but it has one major limitation. The donor pool is limited. So you have a very limited opportunity of having hearts, and also the technology requires very specialized centers. So it's very difficult to scale it across the world, and very difficult to use it in the concept of addressing an epidemic or a future epidemic. The next step is what we say, can we bring an extra value? We can do it with the evolution of stem cell technology, both by taking stem cell from somebody else or actually from ourselves as well. And in these first steps, you can see how stem cells are extracted, usually from the bone marrow, and then they can be processed. But what is unique here, we can add specific values. So here we are teaching stem cells to repair specifically the heart. We call them cardio-restorative cells. And in fact, the chair of this session and other colleagues here in Belgrade have used these cells to inject them into patients. And that was not like last month, that was already a decade ago. So this is a technology that has been evolving and that we have been now using across 3 continents. But the common theme is that bringing these stem cells, you are not bringing building blocks. You are really inviting the diseased heart to start to heal from within, because they are cues that the stem cells are carrying that will be able to guide the heart to go from a disease mode to a reparative mode. And that's how the field is evolving, is what we call healing from within, by understanding how to unlock the innate powers of a diseased organ to repair itself. In fact, that technology of unlocking the message is even further augmented here in solutions that will be even more scalable, where rather than taking stem cells, which are very difficult to culture and scale again, you're just squeezing out of them the regenerative essence. You are distilling down the most important message that can then lead to repair. So here in the electron microscopy scan, you can see cells on the left, and out of them these very small vesicles, which are known as exosomes. Or in Greek, exosome means a particle that is left the main tissue. It's outside the tissue. And you are building essentially a repertoire of nanotherapeutics, which now you can deliver to many, many people. And so that's one way the scalable regeneration will be evolving as we go forward. It will be a stem cell-free, essentially, technology. Just the message of repair will be sent to the diseased organ. And this is not science fiction. This is already being used right now, not just for heart diseases, but also for other conditions, and we're testing them actively right now. But as magnificent all these technologies may be, they are often limited to acting late in disease. Let's say transplantation will be limited just to end-stage disease, but even this more modern technology based on regeneration will be limited to stages where the disease has already manifested itself. And the reason for that is we don't know in advance who among us will develop heart failure. So we are, in essence, reactive in the way we treat the disease. We are reactive because we don't know who are the people at risk. And so we could change that by removing this question mark and essentially go from a reactive disease management mode into a proactive health management mode. And the new terms are risk mitigation, even pre-cure, in other words, treating before the disease has fully manifested. And a field that we are building right now at the Mayo Clinic is, we named it basically disease interception. We are intercepting the conversion of a disease risk pattern to become an overt disease. And so in that space, to understand the risk, you need to do pretty elaborate study, and I'm just showing you an example that is ongoing right now, where we are following essentially, as you can see, almost 10,000 people. We started in a very small community. We did that with roughly the inhabitants around the Mayo Clinic in Minnesota, and we followed around 2,000 people now for 20 years. But then to validate and replicate what we discovered initially, we did it across the whole state of Minnesota in the second validation cohort, which we follow an additional 12 years. And we're now finishing with the validation cohort, which we did across additional states in the United States. And this is also coming to an end. This collective effort, where we follow people for over 70,000 person years, has allowed us to extract a gene for heart failure. And actually, this is the first time I'm presenting this data because they are not yet fully completed, but you will realize from this graph, if you follow on the x-axis years of follow-up, and on the y-axis the risk to develop heart failure, if you are unfortunately a carrier of this bad gene that we call here KK gene, you will unfortunately have a high risk to develop heart failure. And this risk to develop heart failure is similar, if not larger, than traditional risks for heart failure, which are lifestyle risks, such as hypertension, diabetes, or coronary disease. So by being at the verge of identifying an innate intrinsic risk to heart failure allows you essentially to now act before disease has manifested. And that's important because this gene is not rare. If you take here, we drew 100 people, 14 among them will have, unfortunately, this gene. It's very, very common, and it's unusual, actually, why it's so common. That's a story maybe for another day. But by being common and having such a big size effect, where it doubles the risk for heart failure, you essentially, if you remember, we generally have 1 in 4 people developing heart failure in the population. Now you suddenly drop to 1 in 3 people, if they carry the gene during their lifetime, will develop this heart failure. So by the age of 90, 40% that have this gene actually will have heart failure. That's how important this gene is if we are correct in our calculations. So one solution that we have already tested is what we call recoding the cardiac cell. So it's possible today to take the skin of the person that doesn't have heart failure and send the clock back in time, create out of a skin cell a stem cell. Send the adult skin cell to become a stem cell. So it's turning the clock back. And once we have a stem cell, then you can guide the stem cell to become a cardiac cell. And in the cardiac cell, you can use these genetic scissors that were actually mentioned earlier today, the CRISPR-Cas-based technology, which recently received a Nobel Prize. And with these gene editing scissors, you can remove the bad gene and insert the good gene. And the consequence is what you see below, these bar graphs. Modern technologies have allowed us to scan the heart, and we know that the heart that carry the bad gene have these red bar graphs, which are all bad. They are enlarged heart patterns, cardiac death type of patterns, dysfunctions of the heart, and all of them are somewhat blunted, if not completely reversed, if you are able to gene edit properly. Now, gene editing is a sophisticated technology, so we are looking for ways to erase the disease patterns without having to gene edit. And there are ways that we are also successful in that, but this will require some time. So the pattern of the way we are thinking is essentially evolving medicine from what we use to call a disease-centric medicine, where we always were thinking about a disease because actually we did not really know who are the individuals at risk. And now, as we are increasingly knowing them, and this was an example in cardiac medicine, but here in Belgrade, there are wonderful efforts in neurology, for example, that are happening with similar concepts. It allows the pivot from a disease-centric to a health-centric medicine, which is definitely the medicine in a way of the future. And so coming back to the starting point, which was that the challenge of humanity in the years and decades to come will be the widening of the Healthspan-Lifespan gap. I think the common theme and the common impetus for all of us is an equitable global well-being, and that's, I think, the central focus that unifies us all. And in essence, from something that humanity always wanted, which was to live longer, unfortunately, that pattern, as we're understanding now, carries the disease burden. So it's a moment that we increasingly move to finding ways towards sustainable, healthy longevity, which is actually a priority for the United Nations and the World Health Organization, and we do it for measures that will be of benefit for all of us. And in that concept, what we highlighted here are the various ways to direct destiny, and obviously not at the level of whole humanity, as boldly stated here, but more at the example of a singular organ, and by changing organ health span, help potential patients of not becoming patients. That's, I think, the big concept. The field is evolving very fast, and I will finish with this slide. As you recall, earlier in this session, we spoke about space and space exploration. One next frontier will be also the new environments. We live already in the Anthropocene epoch right now, but we think on Earth. Increasingly, we'll be living in extreme conditions beyond Earth. So the unknown and challenge is the challenge of what collectively we call the exposome, or the new exposures. And so we had recently the opportunity to send actually stem cells to space, and we were selected for a project that sends cells from people that have the good gene and people that have the bad gene. And as I mentioned just a few minutes before, We took skin biopsies from both types of people, and we created stem cells. And out of these stem cells, we created beating cardiac cells. Half of these cells went to space, and the other half remain in our lab at Mayo Clinic and serve as what we call the ground control. And those that went to space actually went all the way to the International Space Station. It takes 20 hours, when they were loaded in Cape Canaveral, it takes 20 hours to reach space station. They stay at the space station many, many days, in fact, many weeks. And I would just parenthetically, especially for this meeting, want to highlight, this happened in the spring of 2022. It's the Axiom 1 mission. It was the first mission at the peak of the confrontation between East and West in the spring of 22, where there was a magnificent collaborative effort and where the Russian cosmonauts that were already at the International Space Station unlocked the door for Western crew, which was a crew of civilians. This was the first all-civilian trip to the International Space Station. When the cells came back, we look at their patterns. Again, there is a good and a bad news. The good news is our genetic machinery does work in space. We can transcribe every single gene that we have in our cells. We still don't know, however, are the patterns useful in transcription. As you can see, if you carefully look, the patterns are not at all identical between the ground control that we kept in our lab and the pattern that we got out of space. But we still don't know which one is better and which one is worse. And especially, we don't know if this genetic risk has amplified while being in space or miraculously was erased while being in space. So there are still things to solve, but this is just an example how transdisciplinary efforts are allowing us to really do new breakthroughs as the field evolves. And I'm thanking you for your attention, and I'm finishing with this slide, which is an emblem of the Mayo Clinic as we celebrated 150 years of existence, and that fusion of art and healing, which is in many ways a theme of this meeting, is also highlighted. And I take the opportunity to thank my team at the Mayo Clinic and indeed the Marriott family and their foundation that have made this work possible. Thank you so very much.
Thank you very much. Well, actually, we finished on time with the discussion also, but I allowed this prolong the presentation because obviously it was very, very interesting. And so we have just a few minutes for the discussion and the comments, and the rest of the comments, the discussion, we leave for the lunchtime. So a few minutes. May I ask Professor Terzic as the last presenter? When we saw on a slide with the different geographies and the gap between the lifespan and the health span, it's almost same in every geography. It's 10 years, actually. If you look at the Africa, Western Pacific or states, almost 10 years. Does it mean that we actually applied the wrong philosophy in the medicine, trying to prolong the life with all these facilities like pacemakers, stents, bypasses, pumps, instead of fighting the comorbidities and making more in preventive medicine?
No, thank you very much for the question, and also thank you for allowing extra time. I think this is the crust of the question and requires a societal answer beyond, I think, just an answer from a medical or scientific fields. It's also a cultural and ethical question, but clearly there is an evolution in thinking that while humanity always looked for life expectancy as the main aspiration, there is more and more emphasis on quality of life. And quality of life is, I think, becoming a cultural need and a mandatory almost direction that the fields are going. It is to be seen how societies will evolve in that regard. There is not yet the magic formula. I think countries that have invested significantly in preventive measures are doing particularly well. As you mentioned, they have been able to reduce comorbidities, which is the biggest burden right now. But I think it's an opportunity that we learn from each other, and we purposely cluster the world in a tripartite way to create almost maybe three solutions, or at least engage the globe to think in a tripartite way as a way maybe to collectively resolve it. Thank you.
Thank you. We have one question for the audience. Yeah, please.
Well, just regarding the last comment, and I have, first of all, thank you to all the panelists for a wonderful, wonderful accumulation of knowledge shared with us. And that brings me to whether it's for quality of life or not, we should continue with the science. The knowledge is important to be there, and then we decide whether we want to use this knowledge to, to choose between longevity and or quality of life and so on. But the science should continue regardless. Did you ever find information on that bad gene, that heart failure gene, globally? Is it existing, this gene, in particular parts of the world and not others? And let me just give the other question regarding the cancer. You talked about therapy, cancer therapy. It is passing information now that there is coming out of Russia, China, no, I think it's Russia, that there is a vaccine to prevent cancer. And would you think within your research that it's really viable? Is it possible?
So please, Mr. Terzic, please.
No, you have asked a wonderful question. So the question is really about the frequency of the gene across populations. And we have access to a unique program that has essentially genotyped 1 million people across the world. And the distribution is pretty equal, with the exception of two populations. Interestingly, this gene is extremely rare in Africa, and we still don't know why. And unfortunately, pretty high or higher in Southeast Asia. And of European subgroups, the Finnish group, which has the most historical ancestry in Asia, has the highest percentage of this gene in their population. The mystery is why this gene is so frequent in general. So probably it has another function that we need still to demystify, and why it was sustained throughout evolution is still an unknown.
Could it be epigenetic?
There could be many reasons, but I don't have the answer today.
Okay, Mr. Trbojevic, please. Could you answer that question?
First of all, there are at least 150, even more, cancers, cells and cancers. From the point of view of my talk, where radiation is applied, it is 50% of the treatment require radiation. How do you attack cancer, in my opinion, is you have to go down to the level of cells themselves to see where and what is happening in the body. Everybody is investigating cancers, and there are so many different kinds. You have to see what is the best way. With respect to the vaccines, I think the way they approached the treatment of using the immunotherapy is maybe very promising, but I'm an accelerator physicist, so I was looking at what can I do in the field of radiation, but when I go down deep into the cancer problem, which, by the way, you saw the graph, 1 in 3 has a problem with heart, but cancer is very close, it's 1 in 4. Every people in the world, 3 of them know who in the family or friends had cancer. It's also a very large number of faces where people die.
Thank you. Thank you. So, Mr. Bugay, I would like to ask you, is it feasible nowadays, looking at your data, to go to the Mars? I mean, that should be like 2 or 3 years of the radiation. And how you extrapolate your experimental results, which is acute, actually, measurements to the chronic?
That's a good question, actually. Probably I will split this question in 2 parts. The first one, indeed, we can reach the Mars using some technical achievements. Indeed, engineers say that we can construct a rocket, a ship, nuclear reactors to support life, to support all the systems to reach and return back. But the problem is that the astronauts will eventually become sick. Will it be possible to control all these systems or not? It's still a question. Potentially, if we can take volunteers who can handle this, probably yes. Especially Elon Musk argues, okay, I will do everything. But still, if we think seriously about the extrapolation, there is a gap between acute radiation and chronic, as you properly mentioned. And still, almost no accelerator facility can provide us real data. We tried to construct some setups for using non-target beams to use some secondary radiations around the border of biological defense, but still there is an ongoing process. We cannot say for sure.
Thank you.
So,
thank you very much. We have another question, and we need to finish them.
To Dr. Trbojevic. My question is about the business model. You are building these beautiful cancer accelerators. Probably you have patents on this. And then Siemens or any other company comes and buys this. Do they pay for your patents, licenses to Brookhaven? And then you, as inventor and researcher, do you get part of this? I'm asking because we are dealing with similar things, not in accelerators. I personally have 125 patents, and they are in video coding, and we are having similar issues.
Well, with respect to that is, by the way, Siemens bought Varian, but they stopped doing proton therapy because they are looking only for profits. In the United States, most of the centers are proton therapy, and that's all based on profits in the United States. In Europe, the approach is more social. Local governments invest money. In Heidelberg, Germany, local community invested money. With respect to the patents, I own multiple patents. In the financial part, the laboratory, actually the organization which runs the laboratory Brookhaven National Laboratory has a contract with the Department of Energy, and we have the organization called BSA, which is owning the patents of mine. And if that gets sold on the market, as you were saying, maybe I'll get some percentage of the. I think they raised the number. They raised the number. But I would like to, I don't know, I'm sorry, for Chairman, to move this discussion a little bit into the other direction, because sustainability is, as I said, existence of the planet is in question. So the problem is mainly why can't we see if we can make connections between the different organizations better to solve this problem of energy consumption as burning the fuels instead, and going to the better energy resources which don't make the carbon dioxide as a consequence of energy production. So in China, as you hear the second talk, they are seriously thinking about the accelerator-driven system. I am bringing this up now. You heard the word Weinberg a couple of times in the first session. He was the first one to develop the nuclear energy by subcritical reactor, because people in the world avoid the nuclear energy because of the reactors work in the critical stage, and it can be sometimes can be an accidents, like we had a couple of them in the world, and people are rejecting this nuclear energy, which is actually the only way to solve the energy problem. Because yes, you have the solar and wind energy, but that's very small percentage, as you noticed in the graph shown by our Chinese colleague. That's very tiny percentage. The solution is either in far future fusion energy or the nuclear energy. But with subcritical reactors, this problem of incidents and accidents is avoided. They are subcritical. So you have so much thorium in the world available, and thorium is one of the fuels can be used in subcritical reactor. That's the way to go to solve the problem of the carbon dioxide and the global warming. We have to solve the energy problem. We have to remove the carbon dioxide production, and all these events connected to the sustainability. There are multiple conferences. There was one in Madrid where the concentration was mostly on, in my field, how to sustain the energy. Europe has a very serious problem with energy. It has to be France solved the problem by using nuclear reactors, but there has to be organized way around the world to solve this problem, because we're gonna be going downhill if we don't solve it. It's well, the graph is very scary. If that continues like that, we are going to be in big trouble very fast.
Thank you very much for this talk. And if there is the only answer that came on my mind is why is that? Why we don't have this collaboration and doing much more on a sustainable way to cover actually the nature is profit actually and the war industry. What is the number one pollution resource? It's a war industry. And why the Germany closed first all nuclear plants and then opened again coal plants? Because of the energy, because of the profit, because of the capitalism of the world that we are living in actually. So we need to find out how to motivate actually not only us, the scientists, the humanists, to motivate the politicians also, because they are ruling the world. And I think this is not whole answer actually, but this is the part of the answer that we have at the moment.
Well, I'm sorry to follow. We heard also this morning, follow the money, follow the money. That's another very interesting question. follow the money. How do you approach this? Are you going to look only for the profits, investment from the companies which has more money, as you suggested in the AI? They have money. They should worry about. By the way, the AI required enormous amount of energy. So, and what are they investing to? Even Microsoft, they want to build a nuclear power plant to get this energy for the computers. So that's good. It's not carbon dioxide. That's not not producing carbon dioxide. But my question to the audience and to the people, especially to the first talk, which was very pessimistic and pointing out where we are as a society, is the humanity under attack? Because where are the motives? Is the profit only the motive? Why does society need, as previously after the war, they invested into science and made significant achievements even in the energy? What's the way to do it? Is it by the government putting money aside instead of putting money into the building larger armies and weapons? Can the society put this money into the right direction? Or is it following the money as we heard? Is it possible to get these multi-billionaires? One of them is Musk. He owns more money than 17 countries together. Is it possible to have that part of the money invested into the right direction? Which way are you going to solve the problem? Is it by the governments? Is it by the private business? Because in the United States you have 3% of the people owning 95% of the money. How do you do that? That's the main question in my mind.
Therefore, we very much welcome the presentation of Mr. Detai Zhou, who asked us kindly to prolong the discussion with him due to some language restriction with the translator during the lunch, and the project from China, which gives hope for all of us. I would like to conclude the session and to thank to all the presenters and the audience. Have a nice lunch.